We're starting section 15.1, integration into variables. So now instead of finding the area under a curve, we're looking at volume under the graph of a two-variable function. So this is in calculus of one variable, we found the volume of rotations and so on and so forth. But this time it's just any graph of any two variable functions. We're trying to find the volume under it. So of course we start with Riemann sums, and then we discuss this concept of iterated integrals over rectangles. And that brings up the Fubini's theorem, that all of these help us in the next section understand what our options are to find the volume. Volume under f of x and y, the graph of f of x and y. Let f of x and y be a function of two variables on a bounded domain D in R2. Problem, find the volume of the solid W between the graph of f and the domain D. And so basically you decide the domain D, and then you build walls all the way to the graph. So the cap is going to be the graph of the function, and you finding the volume between that cap and D if you have walls around it. Now, in this section, we're starting to use the rectangular domain. So, and we show rectangular domain with this R equal to A and B times C and D. The rectangular R right here, and you can see that A and B is the lower and upper an x value for that region, and C and D is the lower and upper y value for that region. We use this notation a lot throughout the section and throughout the course, so this is worth looking at one more time. So let's start with the story of basically finding that volume. So how does this work? This picture is a good picture. You can see the domain, and we're making the domain, we're breaking the domain into smaller and smaller rectangles. And you can see it from the top. And over each rectangle, we sort of build a rectangular prism every time. And then, so we estimate with a few rectangular prisms first, then we make the more and more and more, and we look at the limit as basically the number of rectangles grows toward the infinity, and that should gives us the volume. And so back in the day, we would just break down into rectangles. Now we're breaking down into rectangular prisms. Back in the day, we would find the area of the rectangle. Now we're finding the area of the prisms. And again, back in the day, is calculus of one variables, we would find the volume. We would use the function to evaluate the height of the rectangle. Now we're using the function to find the height of the rectangular prism. Okay, so let's do the comparison. So function back in the calculus 1 was y equal to f of x, and it was defined on A and B. Now, of course, when we start in calculus 3, we start with D that is a rectangular shape. That's today's lesson, basically. Later, it's going to be different shapes also. In calculus 3, you basically use z equal to f of x and y on D, which is the domain Uh, this part, the domain part that is not rectangular, it's much more, there are much more variety in calculus 3 than it was in calculus 1. In calculus 1, it was always over intervals or union of intervals and so on and so forth, and not necessarily always closed. So problem in calculus 1 was find area under the curve, and here's find the volume under the surface. The idea was in calculus 1, slice into rectangles of height f of x and width delta x. Here slice into thin prisms of height f of x and y, and base that is delta x times delta y. Riemann sum in calculus 1 look like the sigma I equal to 1 to n of f of a sample point xi times delta x. Here is the double sum I from 1 to n and j from 1 to m of f of a point, a sample point, which is xi star and yj star. And then you multiply that by delta x and delta y. The integral in calculus 1 was integral from a to b of f of x dx. Here we have double integral, and even though this we will see a to b, or here there will be variables like very soon, but when you start writing the integral, you always write double integral over the region D, and then you find the bounds of f of x and y dA. What is dA? dA, soon you will see what dA is, but it's the definition of it. Basically, you soon see how to replace dA with something to do the computation, but the actual definition of dA is the infinitesimal area, versus here was the infinitesimal length. Double integrals over a rectangle. Let's talk about the process of how basically the definition works. Let f of x and y be a function on the rectangle r equal to AB times CD. For now, assume f of x and y is bigger than or equal to 0 on R. Again, every time we start with integration, we start with assuming just area under, and then we expand it to area under minus area over when it's when the function goes below the x-axis. Here's the same thing. You find a volume above the xy axis, xy plane, and then you subtract it from the volume below the xy plane. So you start with that sort of surface, and you partition R into rectangles Rij by dividing AB into n equal subintervals and CD into m equal in subintervals, and basically naming those breaking points as A to be x naught, and then x1 the next one, all the way to xn, that is B. And then again y naught or y0 to be C, and then you increase by delta y until you arrive at y sub m equal to D. So each tiny rectangle is going to be of this shape, xi minus 1 and xi times yj minus 1 and yj. Each rectangle Rij has sides of length delta x, which is b minus a divided by n, that's familiar, and delta y, that is d minus c. See, for x, it goes b minus a divided by n, that's n interval we divided, and for y, we go d minus c divided by m. And then choose a point, Pij, in the rectangle Rij, and so Pij you say xij star and yij star are the coordinates, and it has to be in that rectangle basically. Let Bij be the rectangular prism with the base Rij and height f of Pij. So that again, you use one of the points to create a height, and volume Bij is going to be equal to f of xij star and yij star times delta x times delta y. That is f of xij star yij star times delta a. So this is something to remember, that infinitesimal area is going to be delta x times delta y, and that's equal to volume under the graph of f of x and y, or approximate the volume of the under the graph of f of x and y, and over Rij. So basically, to see where everything is located, again, you divide the length of the rectangle into n, so that's b minus a divided by n length for each piece, and then you length of the height of the rectangle, or the width of the rectangle divided by m. That's the d minus c divided by m is length of each little piece, and then you create n by m pieces in there. And so what happens is that over each piece you choose a point. Here the point Pij is given. We also called it xij star and yij star, and then you go all the way high to hit the graph of the function. That gives you the height, and the height of the rectangle. So the entire rectangle is that the volume of the entire rectangle is that height times that little domain, rectangular domain, which is delta x times delta y, and times the height, which height, if we're going from P all the way to the surface, that's exactly the value of the function at P. Okay, two little other things. Volume of W is going to be basically approximated by the double sum, I equal to 1 to n and j equal to 1 to m of the volume of the little bij's right here, bij's. So if you want to find the entire volume, you just add up each of these rectangular volumes of each of these rectangular prisms, and then and so basically it's just going to be in double sum, because the rectangles they depend on their x and y axis. Basically, it's not just over one. So in calculus 1 it was just one sum. Here is double sum because the two positions are changing, x position and y position. In here, x position and y positions are changing if you want to find each of the rectangles. And then so that's the first thing. And then so what do? We do the limit again. The volume of W equals to limit as both n and m approach infinity. So if you write it this way, it's going to be just an infinite sum over the series, basically, as limit as m goes to infinity and n goes to infinity. You can write it up there to make it a double sum. If the limit exists, then we call it double integral of f over r, denoted by double integral r and f of x over r of f of x and y dA. Again, one more little detail. When you're writing a double integral over region R of f of x and y dA, then that means that limit as n goes to infinity, limit as m goes to infinity of the double sum, first one I equal to 1 to n, and the second one j equal to 1 to m of the volume Bij, which are the little rectangles. And so as you see, something that we haven't done yet is that when there are fewer rectangles, there are more, the approximation has more error, because you see that there are more empty spots or over, either estimation is under or estimation goes over. And when there are more and more rectangular prisms, it gets better and better until it gets very close to the actual value.